Unit 3B will continue our discussion of forces for systems that are out of equilibrium. We're going to learn how to calculate the net force using Newton's second law, and then we will extend our diagrammatic models to include interaction diagrams. Here's a list of all the forces that we saw in our previous class and slideshow. You'll see that most of these were discussed in the PowerPoint previously, but we'll talk about a few more now. The spring force is a force that acts to restore a spring-like object back to its equilibrium position. What makes a spring force unique is the more that you disturb a spring-like object from being at its equilibrium position, the greater the force will be. So for example, if you have some type of bendy object like this one right here, it would normally be sitting at a equilibrium position. That's where it rests when there's no force acting to distort it or perturb it from its relaxed position. But if I pull it back and then flick it, you'll see that it bounces back and forth because a spring force tries to bring that object back to its equilibrium position. Hooke's law is the equation that is used to calculate the spring force. It depends on two quantities: the spring constant, which is dependent on the type of spring that you're dealing with. If it's a really stretchy spring, it might have a lower spring constant, or if it's a really rigid and stiff spring, it might have a higher spring constant. And then the spring force also depends on the displacement from equilibrium. So how far do we pull a spring back, or how far do we disturb a trampoline when we're jumping on it? That will be known as the displacement. And the equation, Hooke's law, is shown down here for several different situations. So in the horizontal case, we might pull a spring left or right. That would mean we're displacing it in the horizontal direction, or giving it a delta x. And so our spring force will be calculated with this equation, negative Ks, that's the spring constant, times the displacement. This negative here implies that the spring force will always act to oppose the displacement that you do. It will always try to restore it back to its original position. However, we could also consider springs in another direction, like the y direction or a two-dimensional vector. So I'll use delta S for that type of displacement. The friction force exists because there are small microscopic rough features of an object, and when an object is in contact with another surface, those rough features will act to cause it to settle in and be harder to move. There are two types of friction. Kinetic friction is the type of friction that is acting to slow down an object that is moving. It always opposes the object's motion. And then there's also static friction, which is occurring for objects that are not moving. That's what static means. So if an object, you try to move it, but it's really hard to get moving, that's probably because it's experiencing static friction. Our equation for calculating the friction force depends on two quantities. It depends on this coefficient of friction mu and the normal force that is acting on that object. This normal force has to have another surface present to exist. So really, the normal force gives rise to the friction force. And if you're in the static regime, you'll use a slightly different set of variables than if you are in the kinetic regime. A few different friction coefficients are given for a combination of different interfaces. For example, if you're driving your car with your rubber tires, those experience a different amount of friction depending on if the road is dry or if it is wet. You'll see that when the road is dry, the friction coefficient is much higher than when it's wet. So a high friction coefficient means there will be a lot of friction. So that covers all the forces that we'll need for Unit 3. Now remember, in Unit 3A, we only dealt with systems that were at equilibrium. That meant all the forces in either the horizontal direction or the vertical direction canceled each other out. But now we will move into situations where an object is out of equilibrium. That basically means that the object will be accelerating. Let's revisit our discussion of equilibrium now for situations where we are out of equilibrium. When we are in equilibrium in the past, that meant that the net force, the total sum of all the forces in their respective directions, was zero if we were in equilibrium. But if we are out of equilibrium, the net force will not be zero. There will be some imbalanced forces that do not balance out with other forces acting in some direction. This means that our net force will no longer equal zero and will now obey Newton's second law, which says that F equals ma. So if there's an imbalanced amount of force acting, that will cause an object to experience an acceleration. And the more massive that an object is, the more force is required to get it to accelerate. Keep in mind, we need to separate out the horizontal forces from the vertical forces. So you'll always want to write a net force or a sum of all of your forces in both the x direction and in the y direction separately. So this slide was shown previously in the Unit 3A notes, and now it's going to make a lot more sense. When we calculate the net force, we need to add up all the forces that are acting and include their direction. That's what this vector arrow means. So there might be a plus or a minus hidden away inside of these vectors. If we take a look at this child being pushed along by an adult, the gravitational force acts down and a normal force acts up. That means this system will not be accelerating up or down at all. It's not like the wagon is floating off into space or falling into the center of the earth. However, when the adult gives a good solid push to the back of the wagon, the child will accelerate and gain speed to the right. Even though there's friction present, the force of the adult is much greater than that amount of friction. So we can draw our free body diagram in this way, and we see that in the x direction, the forces do not cancel. This means that we are not in equilibrium anymore and that this system will experience an acceleration. And now we link up our ideas of motion to our ideas of forces. Forces lead to an acceleration. And that means that we can use our kinematic equations to calculate an acceleration and calculate other quantities about the motion of an object that experiences a non-zero net force. In general, these problems are going to be a little bit complicated, so you'll want to have a strategy in mind for how you're going to solve them. First, you're going to want to figure out if this is a problem that will require you to think about forces or kinematics or both. Then, as we always do in our physics problems, we identify what variables we know and which ones we don't know. What variable are you trying to solve for? That's your unknown. Drawing a free body diagram will really help you figure out which forces are acting in which direction and which ones overpower the other one. Then, once you have all of your forces determined, you can set up a net force equation in both the x and y direction, and this will allow you to solve for the net force. If it is zero, your system is at equilibrium in that direction. But if it's not zero, you will need to set that net force equal to the mass times the acceleration as dictated by Newton's second law. Then, if you have an acceleration, you might need to plug that back into one of your kinematic equations from the previous units. Really, Unit 3B is just an extension of all of the things that we've already learned. So you know how to do free body diagrams, and you're going to have to do those in this unit as well. But we're going to introduce another tool to help you represent force situations called an interaction diagram. When drawing an interaction diagram, it's important to identify what specific object of interest is your system, and everything else will be your surroundings. So in this situation where we have a child in a wagon being pushed by their two friends, we could say that the child and the wagon are our system, and everything else outside of that is in the surroundings. The surroundings might include Earth, the ground, and both of these two friends that are pushing the wagon along. To draw an interaction diagram, first start by drawing your system in the center of the diagram in a dashed line. That will indicate that this is your system, that we are looking at the external forces that are acting on it. Then, you draw all of your objects that are in your surroundings as a box around the system. Sometimes I like to arrange these boxes so that it sort of makes sense in my mind. To me, the earth is down below the child, so that's why I like to put it at the bottom. And the ground exerts a normal force up, so that's kind of why I like to put it at the top. But really, you can arrange these however makes sense in your mind. The next step is to draw arrows between the surroundings and the system. And these arrows need to have a head on each end, indicating that for every action force exerted on the system also exerts a reaction force that is equal and opposite onto the surroundings. These arrows represent the different forces that are acting between these objects. The last step is labeling each end of the arrow with the specific force that is acting in agent-object notation so that we know which agent is acting on which object. For example, you can see that there will be a gravitational force between the Earth and our system. I've labeled this as the force of gravity from the Earth acting on the child in the wagon. But according to Newton's third law, the child in the wagon will also exert a gravitational force on the Earth. There's also a normal force between the system and the ground, and an applied force between both friends and our system. That'll cover everything for Unit 3B. I'll see you in the next one.